So write the problem. Find whether the given characteristic equation is stable or not. Just build the Routh Criterion table. This is a third order equation. You will get 3 roots, 4 columns. Just fill the table. So you will get first 2 tables 60, 66, 0, 0, 0. If you get nth row elements 0, it is an indication that system is on verge of stability. What are the 2 roots which are on the y-axis? 6s square plus 66 is equal to 0. So s equal to plus or minus root 11j. S equal to plus or minus root 11j. So how does the roots looks like? We'll have 2 roots here. Third root, where does it lie? Does it lie on, let's say, a real axis, or let's say, where does the third root lies? Left side or right side? Left side. On the real axis or not on the real axis? On the real axis, because what is the order of the characteristic equation? You will have 3 roots. You will have 2 roots on the imaginary axis. Third root has to be on the real axis, because if it is staying somewhere here, you should have a complex conjugation. Then you should have 2 roots. That possibility is not there. That is, a third root should be on the real axis. Same equation, if I change the term s cube plus 6s square plus 11s plus 6 equal to 0. So just check now the stability. I just changed the coefficient to 66 to 6. Stable system. So what are the equations that we'll get? 1, 11, 6 and 6. 1, 2, 3, 4. 66 minus 6 by 6. 60 by 6. So this is 10. Okay. This is 0. 10 into 6 by, this is 6. Plus, 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 plus. So all are plus. So this is a stable system. This is a stable system. Clear? Now I just change this equation to C. I'm trying to, I will give the same equation by changing the coefficient. S cube plus 11s square plus 6s plus, let's say, 72 is equal to 0. Now check this system, whether the system is stable or unstable. So what are the equations that you will get? Sorry, just change this equation. I think I just wanted to demonstrate the effect of constant. So I think I just missed the question. Just take SQ. Just take this question. I just wanted to change the constant only, nothing else. SQ plus 6s square plus 11s plus 72. Sorry. So I have given three questions. One is coefficient 66, one is coefficient 6, one is coefficient 72. So what are the roots? 111, 6, 72. 66 minus 72 is nothing but 6. So minus 1. Minus 1 into 72 divided by minus 1 is 72. So plus, plus, minus, plus. So basically minus indicates it is unstable system. Unstable system. Now just count the number of sign changes. Plus 2 plus is 0. Plus 2 minus is 1. Minus 2 plus is 1. So you can say 2 roots on right side of imaginary axis. This is how, see sum of the numbers. Somebody has written sum of the numbers. It is not SUM, it is SOMB. Few elements, it is not sum. Don't sum. If all the elements are positive, it is stable. If one of the elements is negative, it is unstable. Don't write it as SUM. Yesterday rules is SOMB, not SUM. No need to calculate the root. I am just asking the questions. But see, and observe the, let's say SQ, observe the name like systems. SQ plus 6s square plus 11s plus 66. SQ plus 6s square plus 11s plus 6. SQ plus 6s square plus 11s plus 72 is equal to 0. See, this coefficient is changing. This becomes Vajja of stability, this becomes stable, this becomes unstable. This is how the characteristic equations changes. So that is what I want to demonstrate here. See, even a small, so maybe some of you might have one question. If one of the coefficients in the characteristic equation is negative, then the system is unstable. Have you heard this rule? If one of the coefficients in the characteristic equation is negative, then the system is unstable. Have you heard this rule? Yes. But I want to show you here, even if all the coefficients are positive, then the system can be unstable. Clear? So don't, let's say, follow the rules. So you have to find out the Routh criterion table and explore. So that is how you have to explore the system. So you can't take, let's say, any shortcuts here. So that is, check the Routh criterion table because it doesn't take much time. No, it takes only so little time. So let's solve this question. Given the characteristic equation below, I don't need to write, just listen the question. Given the characteristic equation below, select the number of roots which will be located on the right side of the imaginary axis. This is a gate question. This is the characteristic equation. Find the number of roots which are lying right side of the imaginary axis. Just fill the table. This is plus. See, I have not written the number. I have just written, let's say, plus or minus negative. So plus to plus is 0 sign change. Plus to plus is 0. Plus to minus is 1. Minus to plus is. See, right, like this, whatever I am doing, you have to do same way. So by looking at this plus, minus, plus, you will get an impression that only one sign change. But when you do that, you will really get there are two sign changes. Indicates two roots on right side of imaginary axis. So there is no limitations of Routh criterion table as such. You can use for so next question. So write this problem. Given the characteristic equation below, s cube plus 6s square plus 11s plus 6kc equal to 0. Find the values of kc for which the system is stable, verge of stability, unstable. This is another way of asking. He will give the kc as a variable. Now you need to find the values of kc for which the systems are stable, unstable, and verge of stability. So what is the answers? Kc can never be negative. Remember one thing, it is a gain. Kc will always be positive. So just build a table. How do you build the table? 1, 11, 6 plus Kc, entire thing is a constant. So 6 plus, so what is the equation? Did I write wrong? 6 plus 6 Kc. So 6 plus 6 Kc minus 11, 66 by 6 is 10 minus Kc. 10 minus Kc is 6 plus 6 Kc. So this is positive, this is positive, this is a question mark, this is also positive. Clear? Don't take this as a negative. This is positive because Kc is positive, no? Now, what is this question mark? So 10 minus Kc greater than 0, that means Kc less than 1, the system is stable. So this, since this is at the nth row, is this nth row or not? 10 minus Kc is equal to 0. The system is Kc equal to 10, verge of stability. So 10 minus Kc less than 0. So Kc is greater than 10. The system is unstable. The system is unstable. Clear? If you try to see, I have based the first problem based on this equation. I know this problem before. That is why I put Kc equal to 0 first. So that means x cube plus 6s square plus 11s plus 6. That is where the system has become stable. I put Kc equal to 10, 66. That is where the system has become verge of stability. I put Kc equal to 11, 72. That is where the system has become. See, look at this equation. I have framed that equation based on that problem only. Clear? And moreover, you can find the roots when the system is verge of stability. When the system is only one case, you can find the exact root. That also totally will not find, but you can find two roots. That is when it is verge of stability. Clear? Now write the next problem. Kc cannot be negative, no? Kc is a controller gain. Gain cannot be negative. Consider the cascade control configuration shown in the figure below. Consider the cascade control configuration shown in the figure below. This is Kc2. The system is stable when Kc2 is What is the answer? 4/3. Just wait, solve this question. I'll come back in 2 minutes. What is the answer? How many of you agree for, let's say, let's say 4 by 3? See, here the catch is Kc2 greater than 4 by 3 is stable. So immediately we'll tend to answer this question as 4 by 3, but the answer is not 4 by 3. Answer is whatever the value which is greater than 4 by 3 is the answer. So that is E by 2. Kc equal 4 by 3 is on Virchow stability. So first thing is just write the, if you replace this entire loop with, let's say, one characteristic equation, then let's say the transfer function for this one is G1. Then what is the characteristic equation? For the standard loop, what is the characteristic equation? 1 plus 0.5 into G1 is equal to 0. But what is G1? What is G1? Case Kc2 into G1. Then what it will become? 0.5 equal to 0. Then what it becomes? 1 plus 1.5 into Kc2 into S plus 2 by S minus 4 is equal to 0. So what is S minus 4 plus 1.5 into S plus 2 equal to 0. So what is this equation becomes? One plus 1.5 Kc2 plus 3 Kc2 minus 4 equal to 0. Okay. Now, what is the Routh Criterion table? This is a first order equation. So let's go to another board and then so S into 1 plus 1.5 Kc2 plus 3 Kc2 minus 4 equal to 0. How many rows you will get? 2 rows. But the 2 rows will directly come from the equation itself. You don't need to do anything. So this is always positive. This is a question mark. So 3 Kc2 minus 4 is greater than 0 is system is stable. So Kc2 is greater than 4 by 3 is stable. Can you call 3 Kc2 minus 4 is equal to 0 as Virchow stability? Can you call this one as Virchow stability? Somebody has told Kc2 is equal to 4 by 3 is Virchow stability. Can you call? No. Why? What is the order of the equation? First order. Where is this uncertainty? This is first order and this is second row. This is first order. So this is not at the nth row. No. Nth row element should be become 0. That is why Kc is equal to 0. It will, Virchow stability is a wrong concept. Why you do not have Virchow stability for this particular problem? So why you don't have Virchow stability for this particular problem? What is virtue of stability? Roots lying on the imaginary axis. How many roots you should have on the imaginary axis? How many roots? Minimum you should have two roots to lie on the imaginary axis. Here, what is the order of the equation? First order. That does a first order has a chance of, so it doesn't have a chance of getting two roots, no? So there is no concept of virtue of stability. So here one more important point is this is a first order equation. So the root will always lie on the real axis only. The root will always lie on the real axis only. So Kc2 greater than 4 by 3 is stable. Kc2 less than 4 by 3 is unstable. Kc2 is equal to 4 by 3 is not virtue of stability, just root at the rate of origin. Just root at the origin. So, and then this is one point. Another thing is answering this question is another important point. When you see 4 by 3, you immediately tend to answer this question as 4 by 3. Because I think half of the class at least could have answered this problem as 4 by 3. But the answer is anything which is greater than 4 by 3 is stable. That means you check 3 by 4. 3 by 4 is less than 4 by 3. For 4 by 3, rough value is 1.33. So what is 3 by 4? Less than 1. So it is unstable. What is 5 by 4? 1.25. It is less than 4 by 3. So unstable. 4 by 3. At 4 by 3, the system is not stable, not unstable, not verge of stability. It is just at 0. So the answer is 3 by 2, not let's say 4 by 3. This is another way of so is everybody, these are the type of problems that you will get in the, let's say, Routh Criterion table. Now let's take another equation. Let's examine this equation. SQ plus 6s square plus 11s plus 6 plus 6kc is equal to 0. Somebody is asking to show me this slide. Can somebody calculate me when Kc is equal to 0, what are the roots? R1, R2, R3. When Kc is equal to, let's say, 1, what are the roots? When Kc is equal to 5, what are the roots? When Kc is equal to 10, what are the roots? When Kc is equal to 15, what are the roots? Can you just do this table for me? This is little bigger exercise, but I want you to, you have calculus with you, right? So you have calculators with you, right? So do you have calculators or not? Otherwise, you have this, if you have mobiles in your, with you, then you have, let's say, calculator soup, this website. If you just, let's say, if you, I just roots of cubic calculator, equation calculator, I just pressed in mobile, then I got, let's say, calculator soup.com. In that one, I am just doing, okay. So first question is one. Remember, this is not important for gate point of view, but I want to tell you some interesting phenomena. First one I got, let's say, -1, -2, -3. Is everybody with me? I can demonstrate on, let's say, this screen, but I'm afraid I may lose the mind. I will lose this screen. -3, -2, -1. So I'll just change the 6 to 6 means 12. So I got this as -4. This as no. When this is 1, you will not. You will get imaginary roots. -1 minus I into 1.4 -1 plus I into 1. When this is 36. What are the roots when it is 5? I am getting minus 5 by 2. Are you getting the same thing or something else? Minus 0.39 plus 2.5, 9 into I. When Kc is 10, you know the roots. Minus 6. When Kc is 15, 15 means 6 15s what? 15, 5, 75, 15, 6, 90, 96. This is 6.5. So does everybody got these roots? Can somebody plot this root? Can you plot this R1 root? So these are 3 roots. If I try to plot the 3 roots, let's say I'm plotting all the roots with different colors. Let's say this is minus 3. This is how this root is moving with change. This is what is with Kc. This is how the root is changing. What is another root? Minus 2. Minus 2. How this is changing? Minus 2. Minus 2 is going in the, let's say, minus 2 is going like this. What is minus 1? Minus 1 started here. So this is how this root is moving. This is how this root is moving. This is how this root is moving. So are you getting how I have plotted with respect to Kc? This is what is called as behavior of roots. Behavior of roots with Kc. This is also called as root locus. This is also called as root locus. What is the other information that you got from root locus apart from, let's say, Routh criterion table? What does Routh criterion? This is basically 3 systems. Why you got a third order equation? Because it is 3 systems it consists of. What is Routh criterion table says is Kc less than 10, the system is stable. Kc greater than 1, the system is unstable. Kc is equal to 10, the system is Varjavstable. This is the only information tells. But it contains 3 systems. Let's say S minus 3 is one, like you have 3 systems. So what does this particular tells you is, so that means this system, that means every root is a one first order system. Every root is a one first order system. So what does this tells you is, this particular system has no effect on the stability. This particular system is always stable with Kc. These are the 2 systems which are making the entire system to go into unstable region when you increase the value of Kc. So basically you are trying to point out it consists of, let's say, system 1, system 2, system 3. It further tells you there is no problem with respect to system 3. System 1 and system 2 are the ones which are throwing the entire control loop to unstable region when you change the value of Kc. Because control loop is nothing but multiple systems in series, no? So you got a third order characteristic equation. That means you have 3 systems in the control loop. Out of the three systems, which is the systems responsible for the instability of the system? So this is called as the root locus. So this is a graphical procedure. Ideally, how do you plot is, you take the characteristic equation and plot the roots for various values of Kc, and then you plot, you will come to know exactly what is happening when you change the value of Kc. So this is not something that you will do in the root locus. Root locus, you have the rules to plot this root locus, but we are not going to take root locus in the syllabus, or let's say in the gate, because it is a graphical procedure, not important gate point of view. But I just tell you the background of the root locus. So basically root locus talks about locus of roots with respect to Kc, is what is the concept of root locus. Just go through the concept and just tell me if you have any doubts here. Just look at this one and understand. If you have any doubt, just let me know. Eliminate this kind of instabilities, you can't eliminate until, because this is the inherent systems. So suppose if heat exchanger is there, heat exchanger is, but it tells you that when you are putting the value of Kc, don't put the value of Kc beyond 10, is what is it tells you. So what happens if I put Kc equal to 11 in the plant is, suppose if the CSTR temperature is increasing, what do you expect the controller is? You should expect the controller to open the cooling water flow rate so that it takes the entire amount of heat. But when the temperature of the CSTR is increasing, if you put the wrong value of Kc, let's say you put 11 as the Kc, then instead of opening the cooling water flow rate, it closes the cooling water flow rate. That is why when you do the control system design in the plant, you don't talk the Kc language, you talk band language. What do you put as band is, you seal the Kc equal to 10 as the upper band, Kc equal to 10 as the 100% of the band. That means you don't have this facility of changing the values of Kc. You lock this as the band. That is why when you open any control loop of, let's say in the plant, you will have 3 variables. Case band, proportional band, which you call it as band, which is inversely proportional to Kc. So that means when Kc is 10, your band is 0. When Kc is 0, your band is 100%. So clear, that is how you adjust in the plant. So that when you all the plants which are already operating now are already control system designed. Like this analysis has been carried out, find out the values of Kc. The upper values of Kc has already been frozen. Even this Kc equal to 10 also you will not use in the plant, because this Kc equal to 10 is coming from the models. Models may not be accurate. So these models are showing that Kc equal to 10 is the one where the system goes to unstable region. But in reality, maybe the models may not be right. That is where Even though I have a flexibility of going KC up to 10, you will lock at 5 itself. That is where you will discuss the concept of Ziegler-Nicholas settings in the frequency response, where if you know the value of Kc, let's say here the value of Kc equal to 10 is the upper limit. Kc up to 10 is stable. Theoretically, in the plant, you should not go beyond 4.5 because this 10 has come from the models. Models may be inaccurate. Models have some loopholes. That is where I don't want to take chance in the plant. No, suppose in the CSTR, instead of opening, it closes the cooling water flow rate, then the entire reactor will explode. Then I need to shut down the plant for 4 or 5 months. Clear? So this is where I think we will see. Even for Kc equal to less than 10, this is where the systems are stable. Up to Kc equal to less than 10, all the systems are stable. But when Kc is beyond 10, I don't have any problem with this third system. I have problem with the 1 and 2 systems. So it tells you the detailed analysis of the systems. So that means which systems you have to be careful in the control loop. Let's say 1 and 2 corresponds to measurement and final control element. Then you have to be careful while operating these things. Clear? I'm trying to explain most of the background theory of the control systems also. So remember one thing, all these things may not be useful gate point or let's say gate point of view and plant point of view also, but you should know how the control systems are designed in the plants, so that you will appreciate when you are operating. Suppose if you are, somebody of you might be operating in the plants, but when you open the plant operations, you don't see Kc 1 by tau height, 1 by tau d. You just see the parameters. What is my band? You will fix, let's say 100% to 0%. But remember, band is proportional, inversely proportional to Kc. I have one problem with respect to band. I will tell that problem also. But in the plant terminology, this Kc will translate to band. But what is a band? Band equal to 100% is, suppose let's take this problem. Kc up to 10 is stable, but in the plant, I don't want to take risk more than 4.5. Where does this 4.5 came? Ziegler-Nicholas settings. Where does the Ziegler-Nicholas settings experience from? Multiple plants. So when I started, let's say 200, 300 years ago, the concept of control, at that time, somebody might have put Kc equal to 10 also. So they have faced a problem. Then somebody realized that Kc equal to 9 is good. Then the Kc equal to 8 is good. That is how the experience from the multiple plants is consolidated and put into theory called as Ziegler-Nicholas settings, which tells you, let's say, whatever the Kc that you get from the Routh criterion table or frequency response. Frequency response does also the same thing. It tells you up to what Kc the systems are stable. So you might get, let's say 10 is equal to, because I want higher Kcs. No, you are always looking for higher values of Kc, because higher values of Kc has two potential advantages. One is it increases fastness of the response. Second thing is it eliminates the offset. Right at the same time, you are not keen on putting very high values of Kc also, because you may lose control on the control. So Kc equal to 10 means you are very much eager to put, let's say 9, but don't put on 9, because this Kc equal to 10 is come from the analysis of the model. So that is why that upper lock is freeze. Whatever the Kc that you got, 45% of that Kc only you have to use in the plant. Are you getting the feel of the things that I'm trying to say, or are you missing in between? So just see, whatever I'm trying to say may not be relevant to for gate or let's say plant point of view, but just keep the things, because you should have always the target of the subject in your mind. When you understand from, let's say, theory to the practical, that is where you understand most of the, let's say, you appreciate the concepts. You just read the theory, will not get the things. You just see the practicals, will not get the things. So always it is important to go theory to practicals. So the plants will operate definitely very different from the things that you read in the textbooks, but they will not deviate from the concept of the principles. The underlying principles will be completely same. That means when you increase the value of KC, the system fastness will increase. That means KC is inversely proportional to band. No, if you are operating the plant, just to see the band, you just change the band from, let's say, 60% to 70%. If you increase the band, the systems will become slow. That is where when you are starting the new plants, when you start a grassroots refinery, you don't start with the band of, let's say, 0%, because band 0% means you are using the highest value of KC. That means don't play the systems when the systems are fast. You have to start when the systems are slow. So because fast systems you can't control, so directly I put KC equal to 4.5. That means band equal to 0. Then the system may go to very faster way. Maybe something will happen in a seconds. So that is why there is a concept called as tuning of the controllers when you start the plant. What do? Is you start with a band 100%. 1 by tau I equal to some value 1, let's say. Tau D equal to 0. Don't use the differential in the controllers. Slowly put 100%. Then what do you see? The controllers are extremely slow. Put 90%, put 80%. Like this you tune. Once you are comfortable with the controller, you leave it as it is. Then you run the plant for 20 years, 30 years with the same values. So no worries. But remember one thing, you don't do all this analysis. The instrumentation is the one, the instrumentation engineers will have, like if you see the IOCL openings, the number of openings for the chemical are less. So a chemical plant, suppose if I am doing a project for a chemical plant, you need, let's say, 100 hours of chemical engineers. Hours means, like generally the project time is measured in terms of how many hours spent for the project. Let's say 100 hours are spent by the chemical engineers. Then 150 hours are spent by the mechanical engineers. The mechanical work is much higher than a chemical work in an operating plant. Similarly, instrumentation work. So that is why when you see the IOCL openings, you see, let's say, instrument engineers, mechanical engineers, and then chemical engineers. You see, always see. And electrical engineers. Electrical engineers generally are very less. You may find one person per shift for, let's say, 4 or 5 plants together. But you have chemical engineers, and mechanical engineering is the highest thing that you need in a chemical engineer, because the entire thing, see, when you visit a plant, you just see the structure of the plant, how much thickness of the pipe is required. All the pipes, when you are routing from the, let's say, one floor to the second floor, you always see these springs, which are, let's say, tensions which are associated with the pipes. All the spring loads, all these systems, everything is calculated by the mechanical engineer. A small mistake in a spring calculation, spring load calculation, suppose if you send a fluid at 50 bar and 400 degrees, if you do not design, like pipe is, let's say your pipe is going something like this. Let's say pipe is going something like this. You have a spring here. Now, if I'm sending a fluid at 50 bar and 400 degrees, you have to calculate how much load this spring should take. If you do a mistake in the spring calculation, the pipe will break in seconds. So when the pipe breaks in seconds, that means the entire refinery should go for shutdown, or the entire refinery will have a fire. So that is why mechanical has, let's say, 1.5 times higher importance in a chemical engineering plants than a chemical engineers. So I think the discussion went in a different direction. So basically what I'm trying to say is instrumentation and control is something that you will not apply in the plant. There is a dedicated team of instrumentation engineers. That is where they will see this entire concept. But then you will ask, why am I reading this entire system? Is you should also know what is it going in the plant, just to have a good conversation with the instrumentation. But you do not own the responsibility of instruments, or let's say whatever the instruments are there, calibration of the instruments, and then operation of the instruments, control loops design, and let's say all this DCS. Thousands of cables are coming from the plant. Each cable is a data point. No, temperature of the CSTR from the plant is coming is a data point. Pressure of the CSTR is coming is a data point. So you have lot of DCS. DCS is distributed control system, which has inputs and outputs. What is input is a temperature of CSTR is an input. Then you will compare with the set point. Then you will send an output signal, which is opening of the control valve. So like this, you will call this DCS. Like a typical hydro treater has a 5000 input, 5000 output DCS channel. So you will talk in terms of instrument engineers will talk in terms of, let's say, what is this DCS capacities, how many inputs are coming, how many outputs are going. Suppose if you are talking about a small plants, if you are working in an R&D, you do not have that much, let's say, inputs and outputs. No, you may have, let's say, we are doing a simple experiment. You may have, let's say, 10 inputs and 10 outputs. Then you don't need a DCS, you need a PLC panel. PLC means when the number of inputs and outputs are very small. So these are some things which is instrument engineers will be talking about, but not important gate point of view, but just feel of the system. So this is how the controllers design and controllers are done in the plants. You do not work on these controls of the plant every day, because these are already, when the plant is starting up, there is a 10 days phase of, let's say, designing of the controllers, tuning of the controllers, everything is done. So that is where the entire things will be taken care. So I think with this one, we are completed mostly the third chapter entire thing, which is the biggest chapter. See, root locus analysis is something which I'm doing for a characteristic equation. So you can take a simple equation. Let's say I will take three systems in series. Let's say 1 by s plus 1, 1 by s plus 2, 1 by s plus 3, and put a controller KC and just derive the characteristic equation, and then you can do which one is going to stable, which one is going to unstable. You have the concept of open loop transfer function and all, but I'm not doing the root locus because gate point of view, there is no chance of getting a question from root locus because it is very less, because it is talking about the root locus, or let's say diagram. So that is where if you are very skeptic, then just practice one root locus diagram. That is what I can say. Clear? So tomorrow also I may take, maybe at the end of the session, maybe I may take one class on root locus. If you are, let's say, not important by the way gate point of view, I do not see any problem from last 20 years on the root locus, because it doesn't make any conclusion like how I cannot ask anything on a graphical picture. No, but to be on safe side, just practice one root locus diagram is what all I can say. Tomorrow's also I'll keep the same time because I have the office till 5 o'clock. So 5:30. So that is why 6 to 7:30 will be fine. So if you do not have any doubts, then I'll close the session here. Any doubts? Yeah, Bordeaux plots are important because I see the gate questions in terms of Bordeaux plots. How do you find the entire PDC use? Like, are you understanding the practical type of, let's say, explaining, or let's say, do you want something else? So because I always love teaching PDC because this is something which actually interesting. But remember one thing, this is something which you cannot practice in the plant also. Because this is something where you have the most of the mass. Somebody who loves the mass will always love the PDC. So I think I will have, so till now, how many classes we completed? 7 or 8 classes. Now I may have almost 7 or 8 classes more, or let's say maximum 10 classes. I have 3 chapters remaining, but all the 3 chapters are small chapters. Okay, thank you all. We'll meet tomorrow. Have a good time. But remember one thing, don't take any chance of, let's say, taking, you should always read most of the topics. So don't take any rest now. So don't take any rest. Wake up at 5 o'clock, sleep at night 12 o'clock, and then when you are walking, when you are eating, when you are going to washroom, anything, you should be always, concepts will be roaming in our mind. So this is already, we are in the mid of November, you have only 2.5 months. Don't take any chance. Don't take any chance. This 2.5 months, just put your hard work from your side. Later on, if the results are positive or negative, let's leave it to God or somebody else. So what I can do is I can put the best efforts from my side is what you can plan.